So we've been looking at the Kalman filter previously, which is the way of performing filtering updates in a linear Gaussian state space model. And here the goal is to look at a simple synthetic one-dimensional example where we can get more intuition for what's going into the Kalman filter. Okay, so here's the setup. We're going to imagine our data here is produced by taking an underlying sinusoid, sine omega of t here. I've actually used a sinusoid with non-zero phase in the example, but a sinusoid nonetheless, and adding to it some observation noise. Okay, that's the way our synthetic data is going to be produced. And the observation noise is going to be relatively modest. It's going to have a variance of 0.1 here. Of course, the sinusoid is between -1 and 1. And so, typical noise values will be something like 0.3 that's added to this, corrupted the sinusoid. Okay, that's our signal. And our goal is going to be to try and retrieve this sinusoid. We're not going to bake in the fact that we've got sinusoidal signal into our linear Gaussian state space model. All we're going to bake in is that there is some relatively slowly varying component of the signal, which is coming from the latent variables, and some observation noise, which then corrupts it. And so you can think of this as analogous to a real situation where there's some kind of slowly varying, perhaps smoothly varying signal out there that's corrupted by noise. You don't know exactly what the properties are of that signal. And so you're just going to use sort of slowness to try and extract it. You're not going to build in a detailed signal model into your latent variables, just the general assumption of slowness. So we know actually how to do this for linear Gaussian state space models by leveraging all the stuff we learned about Gaussian autoregressive models. We're going to set up our latent state. So it evolves according to the formula here. X of t is equal to lambda x of t minus 1 plus some noise. And we know that if we set lambda very, very close to 1, here we're actually going to use the value 0.99. If we set that very close to 1, then we know that each x of t is going to be very much like the x of t minus 1. And we're going to set the noise, so it has variance of 1 minus lambda squared. Because lambda is close to 1, the noise value here is then going to be very small. The variance is going to be quite small. The reason why we've selected this is so that the long run marginal variance of xt, this is going to be given by, the marginal here is going to be given by a Gaussian distribution in xt with some mean and some variance. Put the mean here and some variance. And in the limit, we know as t tends to infinity, if we set things up in this way over here, sigma t squared is going to tend to 1. The marginal variance is going to tend to 1. And the reason we've done that is that's kind of like the variance of our signal. We set things up so the variance of our latent variables are of the same kind of order of magnitude as our signal. The observation model we're going to use is actually going to be the true model, the way that the true data was generated. So the observed signal we're going to assume was generated by taking the latent variables x of t and adding to it noise of variance equal to 0.1. So this will know the underlying observation noise variance here. We're going to assume that. Okay, and we're going to show how this now can recursively process the data one time step at a time on the next slide. Okay, so let's clear these annotations and go to the next slide in the sequence. So here we're going to imagine that we've seen one data point. The observed data are going to be shown in this blue color. That's this point here. This is time step along the bottom axis here. And the ground truth sinusoid, to which we do not have access, is going to be shown in red. So it's starting off at a value of 0.5 here. Great. Okay, so this is just showing the data. So from the perspective of the blue points and the red points, this y-axis is just the observed signal y. Great. We can actually show the inferences on the same plot. And the reason why we can show the inferences on the same plot is because y and x in this example live in the same space. So you remember that yt is equal to x of t plus noise. So y and x in this particular example live in the same space. So the way I'm going to show the posterior distribution at each time step, here this is the posterior distribution at time t is equal to 1 here. The way I'm going to show that is via a little color map, which tells you what the density is for each setting of x. So from the perspective of the color map, the y-axis is the variable xt. Here, xt is x1. I haven't talked so far about how you initialize the Kalman filter. And so let's just spend a couple of minutes talking about that. It's actually really simple. So for the first step, to set up the recursions, you need to compute this thing, the probability over the first variable given the first observed variable, first distribution over the latent variable given the first observed variable, and we can just use Bayes' rule to do that. So we multiply the prior on x, that's the initial state probability of the latent state, times the first likelihood of x1. So that's the probability of y1 given x1, and we renormalize. And again, this is a big exercise in multiplying Gaussians together and completing the square and computing the Gaussian over the first variable. And then once you've armed with that, you can kick off the recursions. So in the present case, what does that distribution look like? Well, the observed data was way up here, but because this guy here, actually I'm using a zero mean prior for this one. So this is going to be a Gaussian in x1 with a mean 0 and a variance 1 actually. Because the prior is zero mean, this is going to drag us back towards 0 on this axis. So the probability mass has more mass down here. It's not tightly coupled to exactly where the data was. Good. Okay, so that's what happens at the first time step, and that's all of the sort of preparatory work we need to do to set off the Kalman filter recursions. So now let's look at how things evolve over time. So first off, the Kalman filter can make a prediction for what's going to happen at the next time step. So here we've done that. We've formed the probability of x2 given y1. And you can see this is doing all of the intuitive things that we thought this would do. It's a bit wider and more diffuse than the distribution here. Remember, this was showing probability of x1 given y1. And then this slice here is showing probability of x2 given y1. So our Gaussian has got a bit fatter. And again, the mean here, it's a bit hard to see, but the mean of this guy is here and this one is here. So the mean is shifted a bit towards 0 in the way that we said it would. Okay, that's our prediction for what's going to happen, our forecast for what's going to happen at the next time step. And here's what then happens. Our data point comes in. Our ground truth sinusoid is again being extended a little bit to show what is going on at the next time step. And we're going to now update that prediction based on that new data point. And this happens. And you can see that the new distribution we get when we see the next data point, if I flick between these two, is a bit tighter. So the variance has shrunk because we become more certain about what's going on. And the mean has shifted to be closer than the forecast, closer to the data than the forecast initially said. So we've made some correction to that mean to take into account that we've seen that noisy data. And then we forecast the next time point, things get more diffuse again. We observe the data and we update. And again, this thing has got tighter and actually moves closer, not only to the noisy data point, but also to the ground truth value. And we keep doing that. We forecast the next variable, we get the observation coming in and we tighten up around that observation. And we keep doing this. So you can see that the noisy data, of course, are noisy realizations of the red curve. And although perhaps isn't obvious, the mean of the estimates coming from the Kalman filter will on average be closer to the red underlying signal, the true signal, than the blue dots themselves. Some of the observation noise will have been removed out. Okay, let's just carry on doing this as this progresses. And you can sort of imagine how this kind of procedure is useful in any online setting where you've got noisy measurements coming in, perhaps from sensors on a robot, and you need to remove the noise from those sensors to compute, say, something like the position of the robot in an environment. And I'll just run this through to the end. Great, okay. And so after 50 time steps, we're going to sort of terminate this experiment. So I want to briefly talk about another application of this, which many of you may well have met before, which was on the lunar landing module. And on the lunar landing module, they were interested in measuring how close they were to the lunar surface, because that's kind of important when you're trying to land on the moon. And the measurements they were taking, of course, were noisy measurements of the distance to the moon. And so in order to remove noise from those estimates, what they did was they built a little dynamical model for the space shuttle, and they encoded that in the latent variables of a linear Gaussian state space model. So to give you a flavor of what that would do is it would describe the way that the position and velocity of the aircraft with respect to the moon would depend on the thrust coming from that aircraft. So just implementing Newton's equations. Or a discretized version of Newton's equations, with some extra noise in there to account for the fact you don't know exactly what the physical constants are in the lunar landing module, for instance. So there'll be some discrepancy between the dynamics encoded into your latent state and the actual true dynamics of the lunar lander. And then they augmented this with a model for the sensors, which modeled the sensors of having Gaussian noise. These are the sensors which measure how far you're away from the surface of the moon. And then they ran a Kalman filter to, in real time, denoise the estimates of their velocity and their position with respect to the moon in order to guide the landing module. And this is very much, a much more beefed up version of this, where red is the ground truth position of the lunar lander module with respect to the moon, and the blue dots are the noisy measurements that you get back from sensors on the craft. So this is a sort of a neat application of Kalman filtering that, of course, was of critical importance as the lander moved towards the moon.